Hi guys, welcome to part 1 of fluid mechanics quick revision notes. First, we are going to discuss syllabus of fluid mechanics. We have fluid properties, fluid statics, fluid kinematics, fluid dynamics, flow through pipe and boundary layer, dimensionless analysis and model similarity in fluid mechanics. In fluid properties, we have bulk modulus, Newton's law of viscosity, surface tension, non-newtonian fluids. In fluid statics, we have buoyancy and flotation, Archimedes' principle of buoyancy, hydrostatic law, Pascal law, manometer. In kinematics, we have streamline flow, continuity equation, vorticity, total acceleration, Lagrangian system, potential function. In dynamics, we have Bernoulli's equation, Prandtl tube, incompressible forced vortex flow. In flow through pipe, we have losses through pipe, laminar flow, pipes in series and parallel, power transmission, Bernoulli equation for real fluids. In boundary layer, we have displacement thickness, momentum thickness, energy thickness, drag flow force, and Blasian relation. And then we have dimensionless analysis and model similarity. So before starting our video, I do have a disclaimer. My notes for fluid mechanics are a bit more of a scribble, so I would try to make it as clear for you guys as possible. I would zoom in throughout the notes and rewrite all those things if it is not clearly written. If you still have any doubt, you can ask in the comment section. Okay, let's start. In fluid mechanics, control volume approach where mass and energy interaction take place. Pressure of air we know is 1.22 kg per meter cube. So in between I do have small short notes written on top of my notes, so I would keep on mentioning that as well. So we know mass density rho is equal to mass by volume. Its unit is kg per meter cube. If our density is constant, then the flow is incompressible, which is in fluid kinematics we study about incompressible flow. And if density is not constant, then it is compressible flow. For liquid fluids are incompressible, and gases fluids are compressible. Gases are compressible. And at 4 degrees Celsius or 39 degree Fahrenheit, we get maximum water density, which is 1000 kg per meter cube. Next we have specific volume, which is reciprocal of density 1 by rho. Specific volume is volume by mass is equal to 1 by rho. Unit is meter cube per kg. Specific weight is weight by volume. Weight we know is mg, so mg by v would be rho g. Its unit is Newton per meter cube. For water, weight is 98.1 kilonewton per meter cube. Specific gravity or relative density is density of fluid by density of standard fluid. So in standard fluid, we usually take water, and density of water is 1000 kg per meter cube. So to calculate specific gravity or relative density of any fluid, we divide it by density of water, we divide it by 1000. Next is, like I have mentioned earlier, my notes are going to be a bit scribbled here and there, but I would try to make it as clear as possible for you guys. So first we have bulk modulus. Bulk modulus is inverse of compressibility. It is equal to increase in pressure upon decrease in volume by volume. So bulk modulus K is increase in pressure upon decrease in volume by volume. So it would be plus of dP upon minus of dV by V, or it is also equal to dP upon d rho change in density by density. This rho is density and this P is pressure. In case of compression, dP is positive, so dV would be negative. And when dP is negative, change in pressure is negative, then change in volume would be positive. This is in case of solid, change in pressure is negative, then change of volume would be positive. And unit for bulk modulus is Newton per meter square, which is also unit of pressure. So bulk modulus is basically K is equal to rho density dP by d rho. Density into change in pressure by change in density equal to plus of change in increase in pressure upon decrease in volume change by volume. And bulk modulus is inverse of compressibility, so compressibility would be compressibility mentioned as C is equal to 1 by K. C is equal to 1 by K, which is equal to inverse of bulk modulus. So it would be equal to d rho by C is 1 by K, so it would be d rho by dP into rho. Rho is density, d rho by rho dP. This is our compressibility. Its unit is meter square per Newton. Okay, then we have bulk modulus for steel is 160 GPa. For water, bulk modulus is 2 GPa, and for air, bulk modulus is 10 to the power 5 Pascal. 1 Pascal is Newton per meter square, and 1 mm is 10 to the power minus 3 m. 1 GPa is 10 to the power 9 Pascal, and 1 ATM is 101.325 into 10 to the power 3 Pascal. These are for some unit conversions. Then for ideal gas, our dP by d rho is equal to RT, and bulk modulus for isothermal gas is equal to rho RT. This is our isothermal compressibility. Then we have adiabatic compressibility. Adiabatic compressibility is noted as K gamma. So gamma is our adiabatic index, so it would be adiabatic compressibility. K gamma would be gamma into KT. So KT is for isothermal gas, isothermal. So for adiabatic compressibility would be adiabatic index into rho RT. Next we have viscosity. Viscosity is resistance offered to fluid flow. And then we have Newton's law of viscosity. So according to Newton's law of viscosity, our tau is equal to du by dy. Tau is directly proportional to du by dy, and our du by dy is basically velocity gradient, or it is also called as shear strain. And our tau is tangential force or shear stress. So tau is directly proportional to du by dy. So tau is equal to mu du by dy, where mu is absolute viscosity or dynamic viscosity. Absolute viscosity or dynamic viscosity. This is basically our Newton's law of viscosity. Newton's law of viscosity. So moving on, our mu we know is absolute viscosity or dynamic viscosity, and mu is also equal to shear stress by velocity gradient. So in this we know that our tau is shear stress and du by dy is velocity gradient, and tau is equal to mu by du by dy. So mu would be tau by du by dy. So tau is shear stress and du by dy is velocity gradient. So our absolute viscosity would be equal to shear stress by velocity gradient. Mu is equal to tau by dy dy. Then if we have a graph if we plot a graph between tau, shear stress, and velocity gradient, so this is for air, mu for air, the graph for tau versus mu del u by del y would be mu. So this is for mu for air, mu for water, and mu for oil. So our absolute viscosity is increasing in this direction. And for boundary layer flow, if the fluid is flowing, then we draw a velocity profile in this manner. So our absolute viscosity increases in downward direction. Next we have few conversion. This is basically your unit conversion. One stroke is equal to 10 to the power minus 4 meter square per second. One poise is equal to 1 by 10 Newton second per meter square, which is equal to 0.1 Pascal second. Mu, absolute viscosity unit, is Newton second per meter square or Pascal second, and its CGS unit is dyne second per centimeter square or poise. CGS unit is dyne second per centimeter square or poise for mu, absolute viscosity. Then viscosity with temperature. So relation between viscosity and temperature for liquid. Viscosity is inversely proportional to temperature because cohesive force is more than molecular momentum forces, and for gases viscosity is directly proportional to temperature. Viscosity is usually due to two forces, which are cohesive forces and molecular momentum transfer. Then we have mu is absolute viscosity. Then we have kinematic viscosity, noted as nu, and kinematic viscosity is equal to mu by rho, absolute viscosity by density. Kinematic viscosity is absolute viscosity by density, and its SI unit is meter square per second, and its CGS unit is centimeter square per second, or stroke is also its unit, and one stroke is equal to 10 to the power minus 4 meter square per second. And few relations are also there. So our absolute viscosity is directly proportional to under root of T for liquids, and our kinematic viscosity is directly proportional to T to the power 3 by 2. Then from here we can say our kinematic viscosity for if there are two fluids, then for fluid 1 viscosity and kinematic viscosity for fluid 1 by kinematic viscosity for fluid 2 would be equal to T1 by T2 to the power 3 by 2. And for ideal fluids, our absolute viscosity is 0, or it is inviscid fluid, and it is incompressible as well. Next we have is surface tension. Surface tension is due to cohesive force. Cohesive force is basically forces acting between same molecules, and adhesive forces are forces between two different molecules. So surface tension is due to cohesive force because of same molecules. So surface tension, denoted as sigma, is equal to Ft by L. Ft is basically tensile force upon length or circumference. So surface tension is equal to work done upon increase in area. And surface tension for water at 20 degrees Celsius is 0.073 Newton per meter. Then we have concept of capillarity. So in a fluid we have a capillary, and its diameter is given as d. So in capillarity there are two concepts, capillarity rise and capillarity fall. So in case of capillarity rise, we have a fluid and in which a capillary is dipped, and this is our level of fluid in the capillary, and it makes an angle theta, and d is the diameter of the capillary tube. So and in case of capillary fall, we have our meniscus and lower meniscus. It makes an angle of theta here, and d is the diameter. So capillary rise and capillary fall are two concepts, and the height with which there is rise or fall is given as h is equal to 4 sigma cos theta by rho gd, where sigma is our surface tension. In case of water, our theta, this angle is 0 degree, and in case of mercury, this theta angle is 130 degree for Hg, which is mercury. So in case of capillary rise, capillary dip into wetting liquid. Wetting liquid are those in which adhesive forces are greater than cohesive forces, for example water. And in case of capillary fall, for mercury, capillary fall occurs in mercury. In case of mercury, adhesive force is less than cohesive force, so it is non-wetting liquid. Next we have excess pressure drop in a water droplet. We have a water droplet, and inside the water droplet the pressure is Pi, and outside it the pressure is P naught, and the pressure inside the droplet is more than outside pressure, so Pi is greater than P naught. So the pressure difference between the droplet and the outside pressure is Pi minus P naught is 4 sigma by d, where sigma is our surface tension and d is diameter of the bubble, water droplet bubble. For soap bubble, Pi minus P naught would be 8 sigma by d. For liquid jet, Pi minus P naught would be 2 sigma by d. For air bubble in water, Pi minus this is P1. P1 is pressure of our air bubble, and P naught would be the pressure of water. It would be 2 sigma by d. Then we have concept for non-Newtonian fluids. So non-Newtonian fluids, we have this formula, which is tau is equal to A into du by dy to the power n plus b. So A is our consistency behavior, n is our flow behavior, b is our yield stress. Okay, and this is our equation for non-Newtonian fluids. And in case our n is 1, and first we have few cases for b is equal to 0. If b is equal to 0 and n is equal to 1, then it is non-Newtonian fluid. Then it is Newtonian fluid. So basically they are saying that when b is equal to 0 and n would be 1, so it would be tau is equal to mu du by dy, which is for Newtonian fluid. We have already studied. So Newtonian fluid we have include water, air, oil. And if n is greater than 1, then it is dilatant, for which sugar, syrup and blood are dilatant fluid. Then we have n is less than 1, it is pseudoplastic. Paint are an example for pseudoplastic. Then if b is not equal to 0, that non-Newtonian fluid is called as Bingham. Bingham. An example for Bingham fluids are jam, butter, toothpaste, So earlier we had studied the graph of tau versus du by dy for our Newtonian fluids. So the graph for Newtonian fluids was like this. So in case of dilating fluids, our graph of tau versus du by di would be du by dy. So in case of dilatants, the graph would be like this curve, and this is for dilatants. For pseudoplastics, graph would be like this between tau and du by dy for pseudoplastics. And for Bingham fluid, our graph would be du by dy. Graph would be like this. It is straight line, but this extra portion is equal to our b constant. Okay,